let me quickly introduce Horace. We already had him as, I think, second or third speaker ever since we started this last year. Horace is part of the PyTorch team, basically working at Meta. Previously, he wrote some very cool blogs, and some of his tweets went viral because they are really insightful, and his takes on things are very insightful. So that's how I first noticed him. He basically recently, I think it was like December, he was working on this maybe a lightweight framework. I don't know how to describe it, GPT-Fast, that basically allows very, very fast inference. And I wanted him to come here and also first time record the talk with him. So happy to have you, Horace. I think you can kick it off, and we'll take it from there. Hey guys, I want to give a huge shout out to HyperStack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing. Basically 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s. You select the images, you select the SSH key you just created, and hit deploy. That's it. Literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough, honestly. The thing they kind of focus on is basically, because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're an individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
Yeah, sounds good. Thanks for having me again. Yeah, so I'm here today to talk about like kind of the work we did on GPT-Fast with some other additions that make it a bit faster now. And yeah, like Aleksa mentioned, it's kind of it's a GitHub repo. I don't really think of it as a library because I think of it more of like a tutorial repo for how to get like fast performance for transformer inference with like very simple code. Basically. So, as I'm sure, many folks are aware, generative AI has basically, completely taken off over the last year. It's, become the only thing that anybody talks about in many cases. And so there have been like a lot of really great libraries for like transformer inference. And the thing is for like generative AI, there's a lot of other different requirements that people want. Like people really care about like small batch sizes. They really care about latency. They really care about quantization. They really care about high performance. And so this has resulted in like a whole slew of like new like projects for these kinds of things, whether they're doing like transformer inference, whether they're doing like, diffusion inference and all sorts of things. And in particular, one particular kind of generative AI that everybody is really into is a text generation. So we have a lot of really great projects like VLLM, like llama.cbp, MLC, that have like gotten like they do a lot of great things, and have gotten like very widespread adoption in the community. But although some of these are built on top of PyTorch, I do think that it's kind of an interesting question about like where does just stock PyTorch suffer, or like where does it not suffice compared to these kind of specialized inference libraries built on top. And so today we're going to try to do transformer inference with stock PyTorch. So the goals here are that we are trying to limit our requirements to basically only PyTorch, as well as a sentence piece, which is like a library needed for tokenization. We'll try to aim for like less than 1,000 lines of code total, and only Python. And finally, we'll try to aim for very good performance, however that's defined. And so let's see how we do at these 3 goals. Yeah. So the first thing we can try is we can just basically implement like transformer inference naively with just like pure PyTorch and try and do inference. And so if you just try running this, you can see that the performance is very bad. So we get about 25.5 tokens per second for Llama 7B. And so compared to like more optimized libraries, like I think in this case, I think like MLC, XLlama can get to closer around like 170 tokens per second in my testing. Oh, and so to clarify one thing, the metric we're optimizing here for is purely like latency. So it's purely, people sometimes call this like token per second per user, and it basically measures like given an input request, how fast, given an input request, like how long does it take to generate like 100 tokens. And so the higher the number here, the better. And this is distinct from what sometimes people will measure it as like throughput, which is not like a measure of latency. It's a measure of like, if you have like, 8 requests at once, then like throughput accounts for like processing all 8 requests at once. And so there are kind of 2 different performance metrics that people look at. And we are primarily looking at latency here. And the techniques for optimizing throughput are a little bit different, but also a little bit out of the scope of this presentation. I can talk a little bit more about that at the end if folks are interested. Yeah, but basically, just regular PyTorch user latency very bad. And so the question is like, why are we so much worse than like state of the art inference performance here? And so the first observation here is that basically the GPU just cannot be fed fast enough. So if you take a look at a profile, what it ends up looking like is you have like very large gap. Like the GPU does a little bit of work, or so you can imagine the CPU like sends this add instruction to the GPU. The GPU completes that like extremely quickly, and before the CPU can go back and tell the GPU to do another instruction, like the GPU is like waiting for all of that time. And so this is perhaps a little bit surprising to folks because like the CPU is basically doing nothing except telling the GPU what to do, and then somehow the CPU cannot keep up. But here's the difference is like the CPU is basically like a single-threaded Python interpreter, and it's just not very optimized for speed and latency. And the GPU is like this super massively like processing thing with like a ridiculous amount of flops. And also everything that runs on it is like optimized to be extremely quick. And so as folks might be aware, like single-threaded performance has not really improved much over the past like 5 to 10 years. And so basically what we see every year is that the GPU gets like 2x faster, while the CPU maybe gets like 5% faster. And so that's why we've kind of more and more, we've kind of found ourselves in this situation where the CPU just is not able to keep up with the GPU in terms of like scheduling instructions. And so if you can't keep up with the GPU, like if sending one instruction to the GPU just results in the GPU waiting for too long, then what can you do? And so the easiest solution here is you basically just send a big chunk of work at once. So you can imagine it as like the CPU, instead of just giving the GPU like, hey, you do an add, you just capture this entire like large group of work. So it's not just an add, it's like you do an add and a matmul and a layer norm and all these things together. And so this way, even though the CPU is like still pretty slow at sending the instructions to the GPU, because it's sending enough work to the GPU to keep it like running at full capacity, we can still end up running things fairly efficiently. And so the easiest way to do this in PyTorch is basically using a torch compile, especially with like mode is equal to reduce overhead. And so admittedly, it is a little bit tricky actually to apply torch compile to text generation. In particular, there's this component called like the KV cache, that like is can be dynamic often in the ways that people implement it. So I remember like I think previously folks have tried applying like torch compile to the Hugging Face implementation of text generation, and they had some like difficulties because of this like KV cache component. And so there's kind of a couple keys here. So one of them is that you need to kind of do this like special setup of the KV cache. In particular, you want to like statically allocate the KV cache instead of dynamically like growing the KV cache over time. And so in this case, in GPT-Fast, we kind of have an example of how to like statically create a KV cache, and then you can like index into it to update. Another part of this is that there's actually two distinct phases of transformer text generation called prefill and decoding. And these have like very different properties between the two of them. So prefill is basically like, imagine you give the language model like a big prompt. Prefill is basically like the first pass over the prompt where it hasn't seen any of these tokens before, and it needs to process all of the prompt tokens. The decode is like after that, you need to do another force pass per token you generate. And so these two phases have like very distinct properties. In particular, the prefill like is much more computationally expensive compared to the decode stage, while the decode stage is much less computationally expensive. There's also just some other like kind of miscellaneous torch compile optimizations that end up helping quite a bit here. And particularly this thing called coordinate descent tuning, which kind of does a little bit of search over some of the kernel options.
Of course, just a quick question. You might get to this later, but I wanted to ask, like, if somebody is not actually a developer of PyTorch and doesn't know these nitty-gritty details and how PyTorch is implemented, which is basically the point of the framework, right? You don't need to know everything. What's the best way to basically optimize someone's code? Is it to just read blogs there like yours and see the advice is there, or like what would you say there?
Yeah, I mean, so I think the main goal of like torch compile is to like kind of automate this as much as possible. But like inevitably, there's kind of a like co-design that needs to be done between like the code that you've written as well as like what the compiler can do. There's like some code that's essentially what I would call unoptimizable. Like the way that it's written is just like not feasible to like optimize by a compiler. This isn't super easy. There's some kind of like general things, like for example, like control flow and stuff like that often makes the compiler's job much harder. The kind of like the more static the graph is, the more reliably that you'll be able to kind of accelerate it with compilation. But yeah, generally speaking, I think like the good first step is basically profiling, and then after that you can like see what's going on from there. I guess I would recommend a blog post I'd written previously called "Making GPUs Go Brr," where basically that kind of like generally the way I would say it is that like there's essentially like three components generally of like deep learning performance. There's overhead, which is essentially like any time spent not running things on the GPU. There's memory bandwidth, and then there's compute. And so in order, and that's also the order in which you should optimize it. So the first thing you should do is you should like take a look at your profile, see if you're overhead bound. If you are, then that's the first thing you need to resolve. Like no other optimization will help before you resolve your overhead issue. And then after that, you can take a look at like the memory bandwidth things. And that's like a bit harder. But yeah, it's a bit more involved there.
Makes sense. Thanks.
Yeah. And so I guess I'll continue on. And so we see that, just applying this results in like a massive boost in performance. We go from like 25.5 tokens per second all the way up to 107 tokens per second. And this is like a, like a 4x increase in tokens. And this is a lot, unsurprisingly. And so there's kind of two main ways that Torch Compile is kind of helping the performance here. And so the first one is overhead reduction. And so I mainly mentioned Torch Compile as a way to kind of apply CUDA graphs, because I think it's often like the easiest way to apply CUDA graphs. But there are admittedly other ways to do this other than Torch Compile. So for example, like PyTorch provides a direct CUDA graphs API that you can use, and some people use this successfully. You can also like do things like porting things into C++ and stuff like that. But the other thing here is actually Torch Compile actually generates like very fast kernels for the decoding stage. And so what I mean by kernels is like the actual things that run on the GPU, like the actual like CUDA kernels that are being generated. Every single one is like generated from scratch by Torch Compile. Like we are not leveraging, in this case for decoding, we are not leveraging any libraries like cuBLAS or Cutlass or like cuDNN or things like that. And so this isn't, just because we're purposely trying to not use any special kernels. It's actually because Torch Compile kernels actually end up being faster in this case during our testing. So in particular,
sorry for interrupting. Do you use Trident as well somewhere in the stack there, or like how do you design those kernels?
So Torch Compile like generates Trident code. So you can think of it like what a compiler does, right? Is a compiler is basically a system that translates from one language to another language. And so oftentimes in C++, the compiler is translating from like C++ into assembly. But oftentimes for like higher level languages, it's not uncommon to see things like you translate from say Ruby into C. And then you apply a C compiler to translate from C into assembly. And so similarly in this case, in Torch Compile, we don't directly generate like PTX instructions. Torch Compile translates from like PyTorch operators into Triton kernels, and then Triton translates from the Triton kernels into assembly. And so that's how we leverage Triton.
Nice. And a follow-up question is, given that Triton is basically maintained by this single guy from OpenAI, I might be like not up to date, but that's my understanding. Like, how do you think about de-risking that part of the critical path, or just like the whole Triton aspect? Are there any discussions of making that unrelated to OpenAI and becoming like a community project the same way that happened with PyTorch, or what's your thinking there?
So I think in general, like we like interact closely with like the Triton teams from OpenAI. And we have like a good relationship with them. But I think Triton has kind of got like it's more than just one person working on it now. and so, for example, we do have like teams in Meta who are kind of like dedicated to working on Triton related things. Yeah, I mean, so like it definitely like is like something we think about. But I think for the most part, we've been like pretty happy with Triton so far. And we're pretty confident in using it for the foreseeable future.
Nice, thanks.
Yeah, I'll continue on the decoding phase. Happy to answer any other questions that folks have. So in this case, like in particular, the special thing here. So you might be surprised. How can Torch Compile generate a faster kernel than cuBLAS? And in this case, it's basically that we actually have like a very special shape during like the decoding phase of inference, where like the batch size is essentially equal to 1. Like we're only processing 1 token at a time. And so if folks are familiar with this, this is not actually a matrix multiplication. This is essentially just what's called like a matrix vector multiplication. And so a matrix vector multiplication is completely what's called memory bandwidth bound. I.e., all of the time is spent like loading memory from global memory into registers. And so my guess is basically that cuBLAS has just not optimized sufficiently for this case. And so you can see here that like for across a bunch of different shapes, the Torch Compile kernels actually have like maybe like a 20% performance increase over the cuBLAS kernels, which is what Torch calls it to. And so these faster kernels are actually like a pretty big component of why GPT-Fast is like so fast. As in, there are like a bunch of other libraries like TensorRT, LLM, or like Llama to CPU or XLlama that kind of have their like own custom, or like also have like reduced overhead, often by moving things into C++. But GPT-Fast, I think in our benchmarking, has generally been faster than those libraries, and that's primarily just because like the kernels we generate are very fast.
Like one question here is, I'm confused as somebody who is obviously not doing this on a daily basis. Like, how does a team of NVIDIA engineers who are literally paid to be building the best possible algorithms for NVIDIA hardware end up not producing something that's as efficient as what you guys can do as external users of their hardware? Like, I'm just trying to understand a bit. Sorry. Even if you can let Horace ask, because answer the question, because it's easier for me to curate like that.
Yeah, I guess I'll give my first take, which is basically just that I think NVIDIA engineers can definitely write a fast memory, like GenV kernel. Like I don't really think that's, or like they definitely have the capability to do so. I think in this case, it's mostly just like a case where the specific workload that like shows up in transformer inference is very different from the workload that they've traditionally optimized for. So for example, in this case specifically, I think for FP16 GenVs, cuBLAS does not actually even have like a specialized GenV kernel for FP16, while they do for FP32. So that would be my guess as to why like the kernels they've generated are not as fast. The other kind of component I'd add here is that in this case, we are also able to kind of like leverage auto tuning at runtime. So like basically for the specific shapes that we look at, we can kind of like tune and like try a couple different kernel parameters. While when building a generic library, it's much harder to do that.
Okay, that's fair enough. It's just that, I mean, they're literally building that support from the hardware level, like FP16, FP8, and all of that from their side. And also transformers have been around since some years now, like 5+ years. And like they do have a TensorRT as well framework. So they are doing this on a daily basis. And so that I'm just trying to, I guess I'm confused on the dynamics, like how it happened. How didn't they come up with something more efficient for this? Even though it's specific, as you said, but they still have teams working on this, and it's in their best interest to support something like this, I guess.
Yeah, I think my general take is just that there's always like always low-hanging fruit. Like especially I think on the level of like especially when you like my personal opinion is like, especially when you kind of look at things at more of like a full stack view, there often are like less people than you would hope that like understand the whole stack enough to be able to like improve things. And maybe I think a canonical example here is like flash attention, where like I think everybody was looking at attention for some time. NVIDIA had spent, similarly has spent quite a bit of engineers optimizing like attention kernels. And it's not just NVIDIA, like like OpenAI, Google had also spent a lot of time like optimizing attention kernels. But I think flash attention kind of like the particular components needed for flash attention just were not put together by one person before I think Triad DAO did it and yeah, flash attention. And I guess like the rest is history there. So yeah, I think there's always this. Sorry, yeah.
That's a great example. Like the market of ideas is not efficient. Basically, it's just like so much to be done yet. And then the example with Trida is amazing. I agree.
Yeah. Yeah, I think it's just always a matter of like, if you understand things, I think deeply enough at some level, I think there's often kind of low-hanging fruit. Okay.
There's a couple of questions from the audience as well. First of all, how is performance for these optimizations on AMD GPUs? We've been talking about NVIDIA a lot, but yeah.
I actually have an AMD slide later on.
Okay, awesome.
Is there another question?
There's one more. Do you have a preference recommendation in terms of profilers from Rafael?
So it really kind of does depend on like what exactly you're doing. So I use the PyTorch profile. So like different profilers are good for different things. So the two profilers that I use the most is I use just like the PyTorch profiler. So if you just search up like PyTorch profiler, you can see that. But then there's also like and so the PyTorch profiler is kind of good at giving you like a high level view of like what's going on in your program and what you're spending your time on. But then there's also like other profilers that kind of dive deeper into certain particular aspects. So for example, like Nsight Compute is like NVIDIA's tooling for analyzing kernels. And so that gives you like way more insight into any like given kernel, like why is it, running slowly and things like that. And so those are probably the two profilers I use the most often on a day-to-day basis.
Awesome, thanks.
Okay. Yes. So step two, after we've reduced overhead, what's next? And so I guess, kind of following my blog post, after you optimize overhead, the next thing you optimize is memory bandwidth. And so if we look at our program, we can see that we're actually like very bottlenecked here by memory bandwidth. So if you imagine the like inference is basically we take our weights and our input. If we take a look at the size of our input compared to the weights, like the weights are so much larger than the input. And so to a rough approximation, you can basically imagine that a transformer inference during decoding is essentially just how fast can you load your weights from global memory into registers. And this provides like a metric that some people call like MBU, which stands for like model bandwidth utilization. The general idea here is if you assume that the only goal of your program is basically to load the weights from memory as fast as possible, like what percentage of that theoretical peak are you achieving? And in this case, you can compute it basically as like the total number of bytes needed for your parameters multiplied by how many tokens you're computing per second divided by the overall memory bandwidth of your GPU. And so in this case, for a 7 billion model, 7 billion parameter model, we have like 7 billion parameters. We have 2 bytes per parameter, and we're able to generate 107 tokens per second. And so on an A100 with 80 gigabytes of memory, we have 2 terabytes of memory bandwidth. And so if we compute our like our so-called MBU, we get 72%. And so this is actually like a very good number for this hardware. Like you're not able to achieve anywhere close to like 100% MBU, even if you're only doing a copy. And so what this means is that basically we are like already very close to the theoretical limit of how efficiently this can run without any other like changes to the setup. And so, given that, we're very close to the theoretical limit, how can we like possibly do better and improve our performance? And so the main thing here is that we can take a look at our like formula and we can change some of these numbers. So we can't really change the number of parameters. Well, we can, but like, it's not that easy to change. And so bytes per parameter really stands out as like the first thing you can decrease. And so in this case, what we can do is quantization, where we convert the FP16 weights into int8 weights. And so now the bytes per parameter goes down from 2 bytes per parameter for FP16 down to just only a single byte per parameter. And so you can see that this gives us a lot more headroom to improve our model's performance. And so in this case, one of the really nice things about using Torch compile is that it's very easy to like modify and implement this like quantization. To some approximation, like this code on the left is basically what we do. We just store the weight as int8, and then before we do the linear layer, we just convert it from an int8 tensor into an FP16 tensor, and then we do the linear layer. And so this is exactly how it's implemented. But Torch compile is able to like transform that into an efficient kernel. Yeah. And so on the right here, we can kind of see the impact of this int8 quantization. So I guess first here, we can see the dark red line and the light red line are torch compile and and eager mode for FP16. And so you can see this is basically the table we had, the figure we had previously, where torch compile was like about 20% faster. But then the dark blue line is torch compile, where the weights are stored in int8. And so you can see that this is like another, close to like 2x performance improvement at the largest scale. And so this is like basically, we're seeing the effects of like requiring less memory to store weights because the weights are 2x smaller, and so therefore we're able to do it this kernel at 2x faster. And so one of the interesting things here is that you actually really do need a compiler here to see the performance benefits. Where if you run this in eager mode without compilers, the performance like drops off a cliff, and the performance here is actually way worse than even just running it in FP16 without a compiler. And that's kind of showing sometimes the nonlinear nature of performance as it relates to a compiler. Any questions?
I'm looking at the chart. I'm a bit confused on the x-axis. Might be a stupid question, but like, what are we looking at there?
Right.
We slowly per second y-axis, and then the x is what?
The x-axis is just like the size of the matmul. So you can see here, like on the left, it's like a k by n weight matrix, and then you have a k hidden dimension for the vector.
Okay,
and
that makes sense.
Generally speaking, the larger of a like tensor you have, the more relatively efficient you can be for the kernel.
Makes sense.
And so applying this kind of end to end, we see about another 50% boost in performance, which is pretty good, because it's just about like another 50% boost in tokens per second. It's not quite like a 2x boost like we would see theoretically, and this is primarily just because it's a little bit complicated, but like there's a lot of like other overheads here that show up more as you increase the speed of your GenV kernels. And so now that we've gotten into 157 tokens per second, what else can we do? And so here, like kind of the next observation we have is that if we want to generate 100 tokens, we need to load our weights 100 different times. So basically, for each token that we generate, we need to load the weights once from memory. And looking at this, you might think that this is extremely wasteful. And so is there any speculative decoding basically allows us to generate 100 tokens while loading our weights less than 100 times. And so the main idea here, the way I think about this, is that imagine you have like a senior engineer who's correct, but he's pretty slow at writing code. And then you have like a junior engineer who's not very accurate at writing code. Like sometimes he makes the wrong design decisions, but he's very fast at writing code. So how do you combine these two to like take advantage of the junior engineer while not slowing down, or like while not generating incorrect code? And so the main idea here is that instead of just having the senior engineer write all the code, you let the junior engineer write like a bunch of code. Like they write 5 pieces of code here, and then you just give it to the senior engineer to review it. And in this case, perhaps the senior engineer sees that the first 3 decisions he made were correct, and the last 2 decisions were wrong. And in this case, you can just throw out the last 2 decisions and tell the junior engineer to like go on and rewrite those pieces of code. And so this is basically the same idea as how it works with transformer inference, where instead of a senior engineer and junior engineer, we have like our base model, which is like the better model, and we have our like speculative model, which is like a smaller, faster to run model. And so basically what you do is you generate like 8 tokens ahead using the smaller model, and then you use the bigger model to verify all 8 of those tokens at once. And because like you can kind of like do all 8 of the tokens at once, much faster than like generating each token individually. This allows you to kind of take advantage of the bigger model while having mathematically identical results to using the big model to generate each individual token. Yeah, and so like one of the kind of benefits of the GPT-Fast is that since it's basically all in PyTorch and it's all in Python, it's very easy to like modify and implement new optimizations like this. So for example, here's kind of like a fully functioning implementation of speculative decoding in about like 50 lines of Python. And so this is like a lot of code. I don't expect you to like read it now, but it's essentially, you know, just Python code in PyTorch. And so I think it's like a lot easier to understand than if it were more opaque. And so the general kind of like benefit of speculative decoding is that essentially the outputs are mathematically identical to not using speculative decoding. But the downside is that the performance of speculative decoding depends on the prompt that you're using. So for example, in coding, where a lot of the tokens are more predictable, you're able to get much better performance than in other cases. So in this case, you know, with our implementation, we get about a 2x performance improvement on Code Llama, but only about like a 1.3x performance for Llama 7B.
Is that, I guess, because code is more easier to predict than or what's
Yeah. Basically, because code is easier to predict. So I mean, you can imagine like it's kind of similar to here, right? Where like if it's like a really easy like refactoring change or something, you know, like in like writing, in like humans writing code, you know, the junior engineer can perhaps like do a lot of changes without making a wrong choice. But if it's like a really hard, complicated area, perhaps the like junior engineer like gets a lot of things wrong. And so depending on the domain, like the effectiveness of this setup will differ. Okay. And so to the person previously who like asked us about running on AMD, one of the cool things here is that every single Trident kernel during decoding is generated from scratch by Torch compile, including like attention and you know, the GenV kernels like RMS norm, whatever. And so basically we can apply all the optimizations we just talked about on AMD GPUs, just like we can apply them on NVIDIA GPUs. And so similarly, you know, we can see like a similar path where at the beginning we start at 22.4 tokens per second. Applying Torch compile gets us up to 76 tokens per second. And then, you know, applying intake quantization gets us another 30%, up to 35%, up to 103 tokens per second. And so this is kind of one of the benefit of like leveraging a compiler-based approach from the PyTorch perspective, because you know, there's been like a lot of investment into like, you know, other hardwares as a PyTorch backend, both on the PyTorch side as well as on the Triton kernel side. And so basically we can kind of apply you know, these optimizations identically to AMD GPUs. There were 0 code changes actually to like run the same code base on AMD.
Nice. Are you observing any trends between NVIDIA GPUs and AMD GPUs, like both the hardware and software, when you put everything on top, like what performance-wise and like cost-wise? Do you have any insights there? Anything you could share?
I think it's hard to say offhand because I don't know what people are paying for these. And so it's also a little bit hard to compare because like transformer inference is like a very heavily memory bandwidth bound workload. So in this case, like what we see with like the like performance, right, is we're getting like maybe 20 to 30% less performance from AMD GPUs compared to the equivalent NVIDIA GPUs, but it also has like 20 to 30% less memory bandwidth. And so like proportionally, I'd say the AMD stack is maybe like 5% less efficient compared to its like 5 to 10% less efficient compared to its compared to like theoretical performance.
Mm-hmm. Got it. And like over the past couple of years, has that performance gap been getting smaller or any
yeah,
observations?
I think AMD has like done a lot of good work on like investing in Triton. I think I'm actually like pretty optimistic about Triton as kind of like a like GPU agnostic language in some sense. In that basically, like, you can take a flash attention kernel written in Triton, and you can apply it both to like NVIDIA as well as AMD GPUs. And so for Torch Compile, because we mostly generate Triton code, most of our optimization is basically just kind of port one-to-one from NVIDIA GPUs to AMD GPUs. And so we've been like pretty pleasantly surprised at how well that's worked out.
That's super cool.
Yeah, so basically, I guess shorthand, I'm optimistic about the ability of Torch Compile to generate efficient code for AMD GPUs, or like using Triton kernels directly.
Nice. The ultimate question: should we buy AMD or NVIDIA stocks? That's the question.
I will defer that question. Yeah. So after other than speculative decoding, what else can we do? The next thing we can do is we can go to Infor quantization. And so in this case, unfortunately, to like actually run the model, we do need custom CUDA kernels for 4-bit group quantized matmul. So Jeff Johnson kind of wrote these for us internally, and they're very good, but they kind of does require more like custom CUDA expertise. And so applying that allows us to get like another 30% performance improvement from 157 tokens per second to 202 tokens per second. And so as far as I'm aware, at least a month or two ago, perhaps things have improved. But last time I kind of benchmarked these, this was basically like faster than a state-of-the-art kind of 4-bit OSS inference, which was typically around 170 to 180 tokens per second.
That's super impressive. And like I know Tim Detmers had some papers on this topic, like how should you distribute the bits if you can choose between bigger models with like 4-bit versus smaller models with like 8-bit or whatnot. And I guess I think the answer from that paper was like around 4 bits actually is more optimal than 8-bit, which is surprising that we can actually represent and not lose information. I'm still kind of puzzled by this finding that like 4 bits actually is enough to have like similar accuracy. That's crazy.
I mean, like we will be going to like 4 bits and 6 bits, I think soon with like new hardware, even in training. But yeah, it is surprising just how far you can push things for quantization. And then also, of course, these things can kind of compose, and so we're able to apply speculative decoding on top of Infor quantization to get like another small performance boost up to 244 tokens per second in a benchmark. And finally, we kind of another way to improve performance is simply to like distribute the performance across multiple GPUs. And in this case, PyTorch also provides tools for tensor parallelism that work with Torch Compile. And so, implementing tensor parallelism here, we see we're able to go from like 7 tokens per second in eager mode up to 47 tokens per second for 8 with Torch Compile for Llama 7dB, and then 55 tokens per second for if you apply int8 quantization on top of that. And so, let's kind of like show how this actually looks like when you kind of put these things all together. So on the left side, and what this kind of looks like in practice, the left side here, we have like what Llama 7B eager running at 25 tokens per second looks like. So it's not it's not very fast. It's kind of slow. You can probably go a lot faster than like the code is going. And so here, on the right hand side, we have so here on the right hand side we have the performance after applying GPT-Fast on top of it. And so you can see this was like way faster at 77 tokens per second. And so in this case, we're actually able to run Llama 7dB at 77 tokens per second when using 8 GPUs. And so, if you go back to like an equivalent model to the initial one and kind of apply GPT-Fast optimization on top of this, we're able to get around 246 tokens per second. And you can see that this is, extremely fast inference. It's pretty, not quite instant, but like pretty close to that. And so let's kind of take a look at like the summary of like our goals here. So overall, we're able to like, for simplicity, it takes about 244 lines to implement the model. It takes about 371 lines to implement generation, along with speculative decoding, and then about 150 lines of Python to implement tensor parallelism. And so this is a total of about 766 lines of code for kind of all the features we talked about previously, like quantization, like torch compile, static KV cache, speculative decoding, tensor parallelism. Performance-wise, we're able to achieve up to 241 tokens per second for Llama 7B, and we're able to achieve about 80 tokens per second for Llama 70B. And so the kind of takeaway here generally is that we can, by using native PyTorch, it allows for both simplicity, ease of use, as well as performance. I think PyTorch has kind of historically always really focused on simplicity and ease of use, but by kind of leveraging compilation techniques on top of that, we're able to achieve all three of these. Okay. I also have some kind of bonus content for like some optimizations, but I'll answer any brief questions now, or I can just bonus content.
This is super impressive. I had a quick question about VLLM. Do you know, like, I didn't go into the depth and like a brief comparison between what you guys are doing and VLLM.
Yeah.
And like you mentioned, you're faster. Like native Torch is now faster than the VLLM. Is that what you're saying, or?
Oh no. So I do want to like mention a specific thing here. Like I touched on this a little bit in the beginning, but like GPT-Fast is very much optimized purely for latency, which I think is pretty interesting, right? Because latency is like what shows up if you're running it locally, like on a single device, and it's also kind of like a end level, like end user metric. Like it affects like how users actually interact with your AI program. But it's also very important in practice for people to optimize for throughput, because throughput kind of affects essentially like how many GPUs you need to service like a certain request load. And so VLLM and a lot of these other systems are really optimized for throughput. And so there's a lot of optimizations like kind of in there that we do not need to worry about because we're optimized for latency. So I wouldn't really say that like I definitely would not say that GPT-Fast is a replacement for VLLM. They're kind of optimized for different things. But like, for example, if you're just trying to like run a single model very fast locally and to play with, I think GPT-Fast would like work very well for that. But if you're actually trying to like, stand up a service, you're trying to like handle like thousands of requests per second, then VLM is definitely a much better choice for that.
Nice. Great point. You did mention in the beginning the difference between the throughput and latency. Do you have any rule of thumb how one should compare that? Like, for example, recently LM6 folks released this SGLang, and oftentimes they just like put throughput. How can you transfer some of those methods and understand the latency of their systems in the background as well?
I think throughput and latency are just two fundamentally different metrics. Like generally speaking, like if you really want like a holistic view of a LLM inference service, you really need both of those metrics in order to have like a good view of the performance. There's no way that can translate throughput there's no way to like directly translate throughput to latency, and this is like an unfortunate reality of performance work. And so, for example, there are like some optimizations you can do that actually like improve throughput at the cost of latency, and like vice versa.
Makes sense. There is a ton of cool questions in the chat. One is, did you deal with Grok so far? So again, one of these, I think they have LLM, like some specialized ASICs or whatnot. The guy used to build TPU at Google, like very, very cool story.
I'll talk about Grok. I think Grok is it's a very interesting piece of hardware in some sense, because basically the rough idea of Grok, and why it's able to achieve like very high tokens per second, is basically like like we kind of talked about. The bottleneck here is loading your memory from loading your weights from like what's called like DRAM or global memory into your registers. And Grok is basically saying like, oh, what if we just put all of our weights into our registers? Like we have enough registers that we can just put every single weight onto our register. And so that's what they're doing. And they're able to achieve like, very impressive like latencies per second, or like a very, very impressive latency. There are like other questions here about like, how practical this really is. Like, the system to do this is like extremely expensive and does not like scale to like many users. But in terms of like pure like single request, like tokens per second, I think like this kind of like specialized hardware can like really shine and have like really good performance.
Nice. I guess that was my question. What are some of the trade-offs that we don't see until we actually go and see the details behind that hardware? Because it looks very impressive to me when I heard him speak and tell some numbers, and like immediately I was like, okay, why is not everybody else doing the same thing? Yeah. Okay, let's see what other questions we have here. Why is there not any word about training? Is the team not too interested on that, or what? I guess this is besides the point of the talk. He was just focusing on latency.
Yeah, I think the brief answer to that is just that training is very different from inference. And if I were to do a talk on transformer training optimizations, that'd kind of be another hour. Yeah.
Rafael asks, how small can we go with the size of the speculative model in speculative decoding? I guess this is just a heuristic, right? There are no hard rules here. I don't know in practice what people use nowadays.
Yeah. So I think speculative decoding is actually very interesting in that there's like theoretically a lot of room to push it. There's a lot of like, improvement. Like the general idea about speculative decoding is basically we need some way to predict what the next token is in a cheaper way, or like the main idea of speculative decoding is if we can predict what the next token is, or like if we can guess what the next token is cheaper than it takes to actually like run the model, if we can guess what the next token is like sufficiently accurately enough and sufficiently cheaply enough, we're able to get speedups. And so in this case, we are leveraging another transformer model to like make the guess, but there's no reason that has to be the case. Like you can use like an RNN. You can use like a totally new architecture. Like for example, papers like Medusa just have like branches off of like the regular transformer model to like predict the next tokens. There's work that like doesn't even use the ML model at all. It just uses like n-gram prediction. And so I think there's a lot of room to like push speculative decoding with like different models. I'd say like practically speaking, people often use like maybe a 10x smaller model if you're looking for like a rule of thumb. Oh, sorry. I do want to like talk about like the couple final optimizations, and then I can answer questions after that. So one of the kind of things we did after the original release was we added like an additional optimization for all reduce, and so this is able to improve our performance by quite a bit. So for example, on Llama 2 7dB, you can see that like previously when you applied 8-way tensor parallelism for FP16. We were only at about 180 tokens per second. But with the new optimizations, we're actually able to get all the way up to 330 tokens per second for Llama 7B when using 8-way tensor parallelism and no quantization. So like for 7dB, we're able to go from 47 tokens per second to 63 tokens per second for FP16. And so, and now if you look at the results, we're able to get all the way up to like 91 tokens per second on Llama 2 7dB at Infor quantization. And so this is like a significant jump over like what our previous performance was for tensor parallelism. And so the main idea here is basically we have like new custom all reduce kernels in PyTorch that are like the idea is like taken from faster transformer initially, but like we kind of wrote our own kernels for this. And so the main idea here is that all reduce is basically just like a primitive for communicating among different GPUs. And the standard algorithm for it is very much optimized for like large tensors. But for smaller tensors, it uses what's like called like a ring algorithm, which is like extremely inefficient in terms of latency. And so we're able to write like different algorithms that are optimized for latency purposes that are able to substantially outperform like nickel for this purpose. And so I think the overall result is that our latencies actually end up being like very good compared to the state of the art. So this was from a blog post that Mosaic published for it was talking about like TensorRT performance and blah, 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 blah. And you can see that our results for GPT-Fast on 8x A100 are about like 20% faster than TensorRT's results for A100 GPUs. And so actually GPT-Fast on A100s is actually able to match the performance of TensorRT's performance on H100s. which I think is like a pretty impressive performance improvement. And so TensorRT is like a common solution that people use for distributed inference, but we're able to match it at least from a latency perspective. Or sorry, we're able to like substantially outperform it from a latency perspective. And another, I think, cool thing that we added to GPT-Fast recently-ish is we kind of extended GPT-Fast to MOE and mixed rule models. And so the main idea of MOE for folks who are unfamiliar is basically like, which stands for mixture of experts. It's basically the idea is instead of having a regular linear layer, you instead have like a bunch of linear layers. Like in this case, like up to about 8 linear layers. And then you take your inputs, you kind of like do some kind of scoring on it to find like the you do some kind of scoring on it to find like to find the experts that are like most relevant, and then you basically just like index. You choose like the weights that those scores correspond to. So maybe in this case, when we take a look at the input, we find that like the first expert and the 5th expert are the most relevant for this token. And so in that case, we simply just like choose to do a matmul. But using like the first weight matrix and the 5th weight matrix. And so this is very simple, I think, or it's pretty simple in theory, but actually getting it to run efficiently is a much different thing. You can see in this case, for law model CVP, it's like another 2,700 lines of C++ and CUDA. And so another thing is that people often use this like a library called Mega Blocks for performance, and so that has like a bunch of custom kernels. There's like a paper about it. It's pretty complicated. But this is kind of just the implementation in GPT-Fast. I think it's a total of about like 150 lines, much of which was spent changing like download scripts. But the actual implementation here is basically just like another 30 lines of pure Python. There's like no custom kernels involved here at all. And so the main idea here is that basically for batch size 1, we are able to just generate an efficient kernel that kind of like fuses this entire operation together. And so if you take a look at performance, we're able to get about 204 tokens per second for 8 GPUs on mixed rule MOE. And if you compare this to like the publicly available providers, this is like much faster than any of the providers have in terms of tokens per second. Sorry, other than Grok, I removed Grok from this comparison because they have very fast tokens per second. But on the providers that are running on NVIDIA GPUs, like we are like much faster than them in terms of tokens per second. I guess I will add once again that in some sense this is not like a fair comparison because we are like purely optimizing for latency while they need to optimize for like both latency as well as the price that they're able to reasonably provide it at. But just in terms of latency, this is like I think pretty impressive performance for like a MOE model. And as you can see, it's like required very little code to support it as well.
Nice. The bit that confused me there, on the y-axis you have throughput now, whereas the whole time you were talking about latency. So how does the GPT-Fast actually compare here with this chart?
The problem is that they use throughput to mean latency on this website, which I think is a bit confusing. But in this case, they mean effectively latency.
Okay, makes sense. Quick question on my side, and we have a couple of hands as well, is you mentioned transformers and you mentioned mixture of experts. How hard is it to optimize with current Torch models, like family of models like state space models, the selective ones that like Mamba, for example, or the recent attentionless transformers like the RNN, like the what's the name, the RWKW or something?
Oh yeah, RWKV.
Yeah.
It's a little bit hard to answer this question. So it really depends, I think, on the setting. So like I guess to kind of or I guess maybe expose GPT-Fast a little bit here. we are not able, like, we're not able to like generate efficient kernels automatically for larger batch sizes. And so that's kind of one benefit of doing like small batch sizes, is that we are able to generate efficiently. But at like larger batch sizes, you know, which kind of you want for throughput reasons, we're not able to kind of like generate kernels automatically in this case. And I think that yeah, so it really depends on the specific model. And I think this is kind of like one of the active areas of like work in general, just across like all of ML compilers, but also in PyTorch. It's kind of like what are the things that we can kind of help automate people for? Because the general solution, I think, when you have like a new custom operator like this, is you basically say, I write a new CUDA kernel that's efficient. And in that case, you know, it's not that hard to like integrate that into PyTorch and things like that. But generating that from scratch with PyTorch is like, or like, you know, using PyTorch compilers is like a much harder task. And I think it's kind of like an interesting area of like investment and research.
Nice. Thanks, Horace. We have a couple of hands. I don't know who is first. Maybe Anthony, alphabetically. Or Anthony just forgot to lower down his hand, in which case Tata can go.
Hey, great talk. So in the start, you showed us a profiler of GPU being not utilized completely, right? Do you have any similar image for the current case after applying all these optimizations?
Like a profile?
Yeah, the torch profiler, I guess, the one that you showed in the start.
I don't think I actually showed a profile trace in the start, but if you're interested in one, I do have some like profiles locally. I don't know if I can, like, but yeah, I mean, like, if you're just curious about in general, like how it looks like, it's just like it's very like tightly packed, and you can like see the each individual kernel being run.
Okay. Okay. So
Nice.
basically, like utilizing GPU to the fullest.
Yeah, it's using the GPU to the fullest. It's like fully saturated. Let me see if I can pull. Do I have? Yeah, yeah, but it's fully saturated, and so utilizing the GPU to the fullest.
Okay. And for the 7B model, what other model did you use for speculative decoding?
I used the tiny llama in my tests.
Oh, okay. Cool. Yeah.
Okay.
Awesome. Ivan has the last question.
Where do you think the next batch of like performance is buried?
Like in like for transformer inference or in general, or
For transformer latency, where do you think next like performance, a big performance improvement or improvements are buried?
or like I guess in like what context, I suppose, like in general, or like for transformers?
For transformer latency, like your GPT-Fast is for like improving latency. So,
Yeah.
how do you think we can improve latency even more?
Okay, yeah, I think in some sense it's like pretty hard because, like, you know, as you can see, like, you know, we're already achieving like very good like model bandwidth utilization, and so that's, you know, giving us like, you know, like you know, if you're already at like 70% model bandwidth utilization, you can only get like 10%, 20% improvement, like even theoretically, and you know, it's very, it may just be impossible to actually achieve that in practice. So I personally think like the most like the biggest like vein of improvement is basically like approaches more along the lines of like speculative decoding. Like I think the roof line there is like I think basically for like non-speculative decoding, I think GPT-Fast is like very close to optimal. Like I don't think that you're going to be able to get like much faster than GPT-Fast. I mean, like, I mean, like, even GPT-Fast, right, is like, you know, we beat like state of the art, but we're beating state of the art by like 15-20%, just purely off of like a kernel generation perspective. So if you really want to like improve performance, I think speculative decoding and kind of techniques like that are, like, in my opinion, have the biggest ceiling for improvement, because the potential improvements are theoretically unbounded there, and so I think it's like with things like Medusa and stuff like that, you're able to like push pretty far in terms of how your performance is.
Nice.
Thank you.
Thanks, Horace. This was super cool. I think we can stop recording, and I don't see any more hands. Anthony still didn't reply, and no questions in the chat.